So that's the Drucker-Prager model. There's also the Mohr-Coulomb model. And for those of you that took my undergraduate geomechanics class, I mean, this is essentially the only one we dealt with. In terms of the principal stresses, we have something like this. Where this phi is a material constant called the angle of internal friction. Internal friction angle. All right. In terms of the invariance, where I1 is the first invariant of the stress tensor, not the deviatoric stress, but the full stress tensor. So it's going to include the pressure components. Where we have I1 and J2 and phi, but we also have now this angle theta, okay? Theta is called the load angle. So I'll talk about what that is on the next slide, but I just wanted to draw real quickly. So if the Drucker-Prager model is analogous to a pressure-dependent J2 model, and I told you in words that the Mohr-Coulomb model is analogous to the Tresca model with a pressure dependence, what do you think it's going to look like? That's my hydrostat. What will the end of it look like? What's the shape? So hexagon. Is it going to be, what's it going to look like then in the third dimension? Yeah, so it's going to have this pressure dependence, right? So something like that. Okay. I don't know what you call that exactly. Hexahedral pyramid or something? Hexamid? Yeah. I don't know what that is. Okay, the load angle then, I'll just write down what it is first. So it's a function of J2 and J3. Its value is always between pi over 6, minus pi over 6 and pi over 6. Geometrically what it is, sometimes it can be convenient to express the location in stress space in polar coordinates. So if we have sigma 1, sigma 2, sigma 3, if we measured the sort of the radius as the distance along the hydrostat, right? So the hydrostat is the line sigma 1 equals sigma 2 equals sigma 3. So if we get, say that's radius xc. Then from there we have a right angle with some radius r to the point in stress space. Then the angle between sigma 3 and that line r is theta, is the load angle. So that's geometrically what it is. And theta is controlled by the relationship of the intermediate principal stresses, that is sigma 1 to sigma 2 or sigma 3. So when sigma 2 is equal to sigma 3, then theta is 60, and sigma 2 is equal to sigma 1, theta is 0. And so a lot of times, you know, in the literature, you might see something that, you know, this material has load angle dependence or something like that. This is what they're talking about. Yeah. What? So xc would be the distance along the hydrostat, okay? But the stress is not going to, I mean, if it lays right on the hydrostat, there's no deviatoric stress. It's all hydrostatic, right? So then the stress is some distance away from there, okay? So the distance at a right angle, right? The distance at a right angle from the hydrostat to the point of stress is r. And then the angle from the vertical is theta. So it's just a set of polar coordinates that you can describe the stress. So a lot of times you'll see, you know, J3 dependence or load angle dependence, and these type of materials are materials that exhibit difference in whether the tensile or the compressive state. So, you know, it's not just the magnitude of the stress, but whether it's in tension or compression, it can behave differently.